All right, I want to review with you guys some strategies on how to simplify trig expressions. We'll also run through some examples in this video of how to verify certain equations are true. But given this expression here on 1a, where I've got the sine of u plus the cotangent of u times the cosine of u, what I would do first is I would change any trig functions that are not already sines or cosines over to something that is in terms of sine or cosine. Notice I've got the cotangent of u. The cotangent of u is equal to the cosine of u over the sine of u. So I would convert that over. Now this cosine of u that's multiplied to that, I would leave that as is, since that's already in terms of sine or cosine. I would also leave the sine of u the way it is and just add that on the front. At this point, I'd follow my order of operations, do a little multiplication first. If I multiply over here, I would have cosine squared of u in the numerator and sine of u in the denominator. I would just bring down the plus sine of u because I haven't done the addition yet. Now I'm ready to do the addition, so since I'm adding fractions, I want to find a common denominator. So if this sine of u is over 1, I can simply multiply together my two denominators. That would give me the sine of u, and then I could form some cross products here. I could start by taking this first diagonal. Sine of u times sine of u gets sine squared. And this other diagonal, I'd have 1 times cosine squared of u. That would be cosine squared of u. So at this point, I've done as much simplifying as I can. And when you've done as much simplifying as you can, you want to try to introduce maybe any trig identities you could use. And in this case, you've got the sine squared of u plus the cosine squared of u. That's supposed to stand out to you because this right here equals 1. So I'm going to plug 1 in the place of sine squared of u plus cosine squared of u. And then in the denominator, I just bring that down. That's sine of u. Anytime you've got 1 over a trig function, then you know a reciprocal identity can be used. 1 over sine of u would go to the cosecant of u because cosecant is the reciprocal of sine. And that's how we would simplify this first one. Another example, part B, we have the tangent of x times the cosine of x times the cosecant of x. Just like I did on the first one, I'd start by taking, in this case, tangent of x and cosecant of x, change those over so they're in terms of sine or cosine. Tangent of x converts to sine of x over cosine of x. That's being multiplied to the cosine of x in the middle, times cosecant of x, that converts over to 1 over sine of x. From here, we've got a lot of fractions just to multiply, so this middle cosine, I might put that over 1. As I multiply through, notice how I have sine of x times cosine of x times 1 on top. So if I wrote that out, it'd be sine of x times cosine of x like that. That's all over. In the denominator, I've got cosine of x times 1 times sine of x. So there's cosine of x, sine of x in the denominator. Since I've got multiplied pieces in both the numerator and denominator, I can cancel anything that is common between the numerator and denominator. So notice the sine of x's go away, the cosine of x's go away. Since all of this stuff cancels out, my answer is going to be 1. All right, one more example of simplifying. For part C here, we're going to take the secant of x minus the cosine of x, put that over the tangent of x. Just to stay consistent, let me change whatever I can over to sine and cosine stuff. So secant of x is the reciprocal of cosine. That means I can write it as 1 over cosine of x. I'd be subtracting cosine of x then, still in the numerator. Denominator, tangent of x, excuse me, converts over to sine of x over cosine of x. Okay, now I've got kind of a mess because we've got fractions within a bigger fraction here. So what I like to do is look at the denominators on the little fractions within the greater fraction. And I like to use this trick, especially when those denominators are the same. I like to multiply the numerator and denominator of the bigger fraction by that, we could call it a common denominator in those little fractions. In this case, that denominator is the cosine of x. So we do that to clear all these little fractions within the greater one. And as I do that in the numerator, I distribute the cosine of x through. When I distribute cosine of x to 1 over cosine of x, the whole point in doing that is to clear the fraction, so all that remains is 1. I'm then subtracting cosine of x times cosine of x, would give me cosine squared of x. That's all over in the denominator. Once again, the whole point is to cancel out these little fractions, so the cosine of x and cosine of x here would cancel each other out, leaving you with sine of x. Now that you've simplified all that, you're in a position to use some identities. You see ones, cosine squareds, or sine squareds. That's supposed to stand out to you as some form of an identity. 1 minus cosine squared of x is equal to sine squared of x. So sine squared of x would replace the numerator. Sine of x is still in the denominator. And if I take the sine squared of x and I divide that by the sine of x, well, basically, this denominator is canceling out, leaving me with 1 sine of x on top. My answer would be just sine of x. So there's a few examples of how to simplify some trig expressions. All right, now let's move on to some examples where we're verifying some trig equations are true, also known as verifying identities. The rule we usually follow with these, as we divide up our two sides, is we work with one side exclusively to make that side look like the other. And in terms of choosing a side to work with, we choose the side that tends to have the most stuff to play with. So it appears on this one, maybe the right side would be a good choice. If I choose the right side, I follow the same rules as I did before when I simplified trig expressions. A lot of times you want to change things over in terms of sine and cosine. But if I'm playing with the right side here, everything is already in terms of sine or cosine. So I might go ahead and multiply this all out. If I do a little foiling, you'll notice multiplying the first terms, I get 1 back. Now, if I multiply the outside terms, I get positive sine of alpha. If I multiply the inside terms, I get negative sine of alpha. So understand that those are going to cancel out. So really, I don't need to bring those down in the next step. Instead, I can skip ahead to multiplying the last terms. Negative sine of alpha times positive sine of alpha would be negative sine squared of alpha. Now keep in mind, I'm trying to make this right side look like the left, so I can kind of sneak a peek to see where I'm going. But at the same time, if I'm consistent with what I did simplifying trig expressions, I'm trying to use an identity at this point. I see a sine squared, I see a 1. I'm subtracting those ideas. I know that's equivalent to cosine squared of alpha. And normally I would be done at this point if I'm just simplifying, but trying to make this look like the other side. Notice the other side, you've got 1 over secant squared. That means I'm basically trying to get to the reciprocal of secant squared. So the reciprocal of secant is cosine. I'm right there at this point. So all I have to do to finish this off is write 1 over secant squared of alpha, since that's equivalent. I've now verified that this original equation, or if you want to call it identity, is true. So for our part B example here for our verifying problems, I split up my two sides and I work with the side that's got the most to play with. Obviously that'd be the right side on this one. So thinking back once again to how I deal with trig expressions, a lot of times I like to change things over so that it's in terms of sine and cosine. If I do that on this one, I could start by writing out my numerator as 1 plus 1 over cosine of x. since that's an identity that's true with the secant. And in my denominator, I would leave the sine of x, since that's already in terms of sine and cosine. I add that on a tangent of x, which is sine of x over cosine of x. And now I've got a pretty complex fraction to work with. I've got little fractions within the greater one. So, like the example I did earlier, when I was just simplifying, I like to try to follow this rule where I look at the denominators that are present within the smaller fractions, especially when these are the same. I like to multiply both numerator and denominator by that denominator. So here it's the cosine of x. When I do that, in the numerator I've got to distribute through to each term. So distributing through to each term, starting with this 1 I'm multiplying to, I get the cosine of x plus, remember the whole point in doing this again is to cancel out the fractions. This cosine of x cancel out, leaving me with only the 1 on top. In the denominator, same thing, distribute the cosine of x through. As I multiply the cosine of x to that first term being sine of x, I'd have sine of x, cosine of x, then plus cosine of x cancel, leaving me with sine of x. Looking at the point we're at now, a lot of times when we do all this simplifying, we're looking to use an identity, but no identities are standing out because we don't have cosine squareds or sine squareds. But since we have a fraction, a lot of times we look to try to cancel some things, and the only way we can cancel stuff is if everything is factored out. So I'm going to leave my cosine of x plus 1 as it is in the numerator because there's nothing I can do with that. But notice the factoring that can be done in the denominator. We've got a sine of x that we can take out. If you take a sine of x out, take the sine of x out of this first expression, cosine of x would be left, plus take the sine of x out of the second term, 1 would be left. Now notice what has happened because everything has been factored. You have a cosine of x plus 1 and a cosine of x plus 1 as common quantities you can cancel out. In the numerator, 1 would be left. In the denominator, sine of x would be left. Extend this line a little bit further. We're one step away now, because you'll notice 1 over sine of x, that 1 on top means take the reciprocal of the bottom. Reciprocal of the bottom sine would be cosecant. And hey, what do you know? That's on the other side. So we verified that that's true. All right, new problem to verify here. Cosine of x over secant of x plus sine of x over cosecant of x equals 1. We're going to verify this one. Probably want to work with the left side. Has the most stuff to play with. If I'm consistent and I change things over in terms of sine and cosine, I would have the cosine of x over, well, secant is 1 over cosine of x, plus I'd have sine of x over, cosecant would be 1 over sine of x. All this is supposed to equal 1 on the other side. Actually, I don't usually introduce that yet, do I? I usually just bring that through. At this point, you've got two separate fractions to work with. Each have a fraction within a greater fraction. So using the trick from before, for this first fraction, I'm going to multiply the top and the bottom by the cosine of x. And for the second fraction, I'm going to multiply the top and the bottom by the sine of x. Right, after all, that's my denominator right here. So in doing that, for this first fraction, you got cosine times cosine, so there's cosine squared of x. In the denominator, you've got cosine of x times 1 over cosine of x, the whole point being that these guys will cancel out and you're just left with 1. So that's pretty nice. This is just the cosine squared of x over 1, or cosine squared of x. Plus, similar thing happens here on the second fraction. In the numerator, you've got sine of x times sine of x, that's sine squared of x. Denominator, the sine of x's would cancel each other out, leaving you again with just a 1. So essentially, we've got sine squared of x. As we simplify that all down, identities should stand out. Since you have cosine squared plus sine squared, we know that that equals 1. So that one wasn't too bad to verify. Part D here, it really doesn't matter which side you want to work with, and that's true with any of these problems, but this one for sure, neither one is more complicated than the other. So for purposes of this example, I'll just choose the left side. And if I'm going to choose the left side, actually what stands out to me is this is a double angle formula scenario that I'm playing with, so you could be creative and use a double angle formula to help you verify. But if you don't see that, and we just kind of hold true to what we've been doing, this is a problem where I might, if I'm working with the left side, take a peek at the right and try to see where I'm going. I'm trying to turn this into something that only has cosine in it. And right now on the left side, I've got this sine squared that's kind of hanging me up. So is there a way to get rid of that sine squared of x so that I only have cosine squared of x stuff? Well, one way to do this is use an identity to start. I've got the cosine squared of x that I'm just going to bring down here. I'm going to subtract for this sine squared of x. I'll change colors here so we can distinguish a little bit better. Sine squared of x is 1 minus cosine squared of x. So I'm going to substitute that in. If I substitute that in and I do a little algebra with some distributing and collecting of like terms, notice what happens, changing my signs here. Well, I end up with a -1, obviously, which for where I'm going, I want a -1 here at the end, so I'll write -1 here at the end of my expression. And I've got a couple of cosine squares that apparently I'm adding together. So I've got like terms there. I've got 2 cosine squared of x minus 1. That's what I'm trying to get on the right-hand side. So it looks like we're good to go. All right, so we got quite a few verifying examples here. This is the last one of the bunch, part E. If I choose a side to work with, once again, it doesn't matter, but I would probably choose the left since I got some fractions to play with, and normally that intimidates people more. So if I choose the left-hand side and I've got fractions to work with, which are being subtracted, I should probably find a common denominator. So the way we do that, one more time, I take my denominators, I basically multiply these ideas together. As I multiply those ideas together, got a new fraction I'm creating down here. Probably not a bad idea to FOIL these out. If I FOIL these out, first terms go to 1. This is another example where the outside and the inside terms would end up canceling, so all you would need to write at this point is what you get when you multiply the last terms. Negative sine of x, positive sine of x, negative sine squared of x. That gives me my denominator. Now I start looking at these cross products. First diagonal, I would take 1 times 1 plus sine of x. Obviously, I would get the 1 plus sine of x back. Go ahead and group that right now, just to show that that's my result for the first part. Understand I'm subtracting cross product here. For this second diagonal, you've got 1 times 1 minus sine of x. Well, that's going to be 1 minus sine of x. Parentheses on the second diagonal product is a little more significant because we are subtracting. Since we're subtracting, we're going to have to distribute this negative through. So the negative gets distributed, that changes some signs, and if you notice what happens trying to collect like terms, the 1 and the -1 go away. And we are left with a couple of like terms, sine of x, that we add together. We get 2 sine of x over, well, at this stage, you know, you could leave this as 1 minus sine squared of x. But look at where you're going. You're trying to squeeze a 2 out of this, which now we do have a 2. That's good. But we've got these other 2 different functions, secant of x, tangent of x. So since I don't see anything over here with a denominator that's subtracted, maybe, to save myself a step, I could use the identity for 1 minus sine squared of x. That's cosine squared of x. Now if you consider where you're going, and this is really important on this one to see the next step, you've got 2 times secant. Well, what's secant? Secant is 1 over cosine. Times tangent. Well, what's tangent? Tangent is sine over cosine. So I've got a sine that needs to be in the numerator. I've got some cosines that need to be in the denominator. See the arrangement I have right here. A sine in the numerator, a couple of cosines in the denominator. If I break this up, 2 times 1 over cosine of x times sine of x over cosine of x. Right? If I multiply all this out, I get right back up to this step. That's how I can check and confirm that this is true what I'm doing. But I'm doing this with the purpose of trying to turn it in to the other side. I've now accomplished that goal because I got that 2 in front. 1 over cosine becomes secant of x, and sine of x over cosine of x becomes tangent of x. That one was a little tricky because you do have to really take note of what's happening on that right side.